Have you ever looked up at the night sky and wondered, why? Why are we all here? What's out there? And how does it all work? Well, you're certainly not alone. Hello, everyone, and welcome to the Big Why. I'm just as curious as you are about the universe and everything in it. From the depths of the ocean to the furthest reaches of space, no question is too big, no topic too strange for us. We'll crack open the mysteries of black holes, journey to the edge of the universe, and explore the mind-blowing discoveries that are changing our world. So if you're ready to unleash your inner scientist, ask the tough questions, and explore the universe alongside me, then buckle up, and let's ask why. Now, before this video begins, I would like to make a quick note for the audience. You may recall a previous video on this channel originally titled, What is Space? Well, I've since updated that to What is Outer Space to avoid any confusion. That's because outer space, the realm of stars and galaxies, is slightly different from the boundless 3D extent we'll be exploring today. We experience space every single moment of our lives, yet it remains an enigma. We can't see it, touch it, or taste it. So what makes us so certain it's even real? Who first conceived of this elusive idea, and what have we learned about it since? In this video, we'll tackle these mind-boggling questions and delve into the minds of the brilliant scientists who dedicated their lives to unraveling the mysteries of space. And who knows, perhaps the next groundbreaking discovery about space will be made by someone watching this video right now. Now, what exactly is space? Space is a three-dimensional continuum, a vast canvas where positions and directions unfold. Classical physics often simplifies this to three linear dimensions: up and down, left and right, forward and backward. But modern physicists paint a more intricate picture, weaving space and time together into a boundless four-dimensional tapestry called space-time. This concept of space is absolutely fundamental to our understanding of the universe. Yet, even the brightest minds grapple with its true nature. Is space a tangible entity in itself, a mere relationship between objects, or simply a framework for our thoughts? The debate deepens when we consider non-Euclidean geometries, where space curves and bends rather than remaining flat. Einstein's theory of general relativity revolutionized our understanding, revealing how gravity warps the fabric of space itself. Experiments have since confirmed that this non-Euclidean model more accurately reflects the shape of the universe we inhabit. The very nature of space has been a source of philosophical debate since the days of ancient Greece. Thinkers like Plato and Aristotle pondered the essence of space, grappling with questions that still resonate today. In the Renaissance and the 17th century, as classical mechanics emerged, these questions found new life. Isaac Newton, a towering figure in science, envisioned space as an absolute entity, existing independently of any matter it might contain. However, not everyone agreed with Newton's view. Gottfried Leibniz, another intellectual giant, proposed a radically different concept. He saw space not as an independent entity, but as a network of relationships between objects, defined by their distances and directions. In this view, space was relative, a consequence of the matter it held. The 18th century brought further challenges to our perception of space. Philosopher George Berkeley questioned whether we could truly perceive spatial depth, suggesting that our sense of space might be an illusion. Immanuel Kant, a groundbreaking metaphysician, went even further. He argued that space and time weren't simply derived from our experience of the external world, but were innate structures within our minds, shaping how we perceive everything around us. Galileo Galilei, a pioneer of modern science, challenged the long-held Aristotelian and Ptolemaic views of a geocentric universe, where Earth was the stationary center. Instead, he championed the Copernican model, proposing that the Sun held the central position with Earth and other planets orbiting it. This revolutionary shift raised critical questions about motion. If Earth was in motion, the Aristotelian notion that objects naturally tended towards rest was shattered. Galileo sought to demonstrate that motion, particularly circular motion, was as natural to celestial bodies as rest. This idea challenged the Aristotelian belief that objects were drawn to their designated natural place, paving the way for a new understanding of motion in the universe. Galileo's groundbreaking work, alongside the philosophical inquiries of his predecessors, laid the groundwork for the scientific revolution. It was a time of radical transformation in our understanding of the universe, culminating in Isaac Newton's landmark publication, Principia Mathematica, in 1687. Newton's theories about space and time revolutionized physics, providing a framework to explain the movement of objects and laying the foundation for our modern understanding of the universe. René Descartes, a philosophical trailblazer, sought to replace the prevailing Aristotelian worldview with the new understanding of space and motion governed by natural laws. He aimed to establish a metaphysical foundation, a mechanical explanation for his theories of matter and motion. Descartes envisioned space as a Euclidean structure, infinite, uniform, and flat. This space was intrinsically linked to matter, serving as its container. In essence, matter and space were inseparable, with no room for the concept of empty space. His theories about space were deeply intertwined with his broader ideas about the body, mind, and matter. Descartes is renowned for his famous dictum, cogito ergo sum, I think, therefore I am. This highlighted the primacy of thought and doubt as the foundation of existence. As a rationalist, Descartes believed that knowledge about the world stemmed from our capacity for reason rather than from our experiences, as empiricists would argue. He also proposed a clear distinction between the body and mind, known as Cartesian dualism, which has had a profound and lasting influence on Western philosophy. In essence, Descartes' revolutionary ideas about space were part of a broader philosophical framework that sought to explain the universe through reason and natural laws, paving the way for the scientific advances of the Enlightenment. The debate over the nature of space continued into the 17th century with two towering figures, Gottfried Leibniz and Isaac Newton. Their opposing views sparked a philosophical duel that echoed through the ages. Leibniz, a brilliant philosopher and mathematician, rejected the idea of space as an independent entity. He saw it as a collection of spatial relationships between objects, distances, directions, and relative positions. In his view, space was a consequence of the objects it contained, not a separate entity in itself. Imagine a family tree. The relationships between family members are real, but they don't exist without the people themselves. Likewise, for Leibniz, space was an abstraction derived from the relationships between objects, not a fundamental reality. Newton, on the other hand, championed a different perspective. He believed that space was more than just relationships. It was an absolute entity, existing independently of matter. His belief was grounded in observation and experimentation. He argued that the concept of inertia, where objects resist changes in motion, required the existence of absolute space as a reference frame. Newton's famous bucket argument aimed to prove his point. Imagine a bucket of water hanging from a rope set spinning. As the water begins to swirl, its surface becomes concave. Even when the bucket stops spinning, the water continues to curve inward. Newton argued that this phenomenon couldn't be explained solely by the relative motion between the bucket and the water. It had to be due to the water's motion relative to something else, absolute space itself. This bucket argument held sway for centuries, seemingly confirming the existence of absolute space. But the debate didn't end there. As we'll see, the 20th century brought new perspectives and a deeper understanding of the intricate relationship between space, time, and matter. The 18th century brought a new perspective on space with the influential philosopher Immanuel Kant. He proposed a radical idea. Space wasn't an external reality, but rather a property of our minds, a way in which we organize and perceive the world around us. Kant's theory of space was a cornerstone of his broader philosophy of knowledge. He argued that our understanding of space wasn't derived solely from experience, but was also a fundamental part of how our minds are structured. In other words, we're born with an innate sense of space that shapes our perception of the world. He believed that knowledge about space is synthetic, meaning it goes beyond simply defining the terms involved. For example, the statement, "all triangles have three sides," is true by definition, but the statement, "This object is located 5 feet to my left," requires an understanding of spatial relationships. Kant also argued that our knowledge of space is a priori, meaning it doesn't depend on sensory experience. A blind person, for example, can still understand spatial concepts like distance and direction through their other senses. This suggests that our understanding of space is not solely derived from sight, but is a fundamental aspect of how our minds are organized. In essence, Kant's theory of space challenges us to reconsider the very nature of reality itself. It suggests that space isn't simply a neutral container for objects, but an active participant in shaping our perception of the world. This revolutionary idea laid the groundwork for further exploration into the subjective nature of our experiences and the relationship between mind and reality. In the 19th century, a new chapter in the story of space unfolded, challenging the very foundations of geometry itself. For centuries, Euclidean geometry, as laid out by Euclid in his Elements, had reigned supreme. It was based on 5 postulates, seemingly self-evident truths about lines, points, and angles. One of these postulates, known as the parallel postulate, sparked a mathematical revolution. It stated that given a line and a point not on that line, there's only one other line that can pass through the point and never intersect the first, a parallel line. For centuries, mathematicians accepted this as a given, but some questioned whether it was truly a fundamental axiom or a theorem that could be proven. In the 1830s, 2 mathematicians, Janusz Bolai and Nikolai Lobachevsky, independently shattered this assumption. They explored a new type of geometry, hyperbolic geometry, where the parallel postulate didn't hold true. In this strange new world, an infinite number of parallel lines could pass through the same point. Triangles had angles adding up to less than 180 degrees, and the ratio of a circle's circumference to its diameter wasn't the familiar pi. In the 1850s, Bernhard Riemann took this revolution further with his theory of elliptical geometry. In this model, there were no parallel lines at all. Triangles had angles adding up to more than 180 degrees, and the circumference to diameter ratio of circles was less than pi. These non-Euclidean geometries weren't just mathematical curiosities. They had profound implications for our understanding of space. It turned out that space wasn't necessarily flat and uniform, as Euclid had assumed. It could curve and bend, taking on strange and unexpected shapes. This realization paved the way for Einstein's groundbreaking theory of general relativity, where gravity is seen as a curvature of space-time. The exploration of non-Euclidean geometries opened our minds to the possibilities of a universe far more complex and fascinating than we had ever imagined. It was a testament to the power of human curiosity and the relentless pursuit of knowledge, even when it challenges our most deeply held assumptions. In the wake of non-Euclidean geometry, a new question arose. Could physical space itself be curved? Carl Friedrich Gauss, a brilliant German mathematician, pioneered the idea of empirically investigating the geometry of space. He even contemplated measuring the angles of a vast stellar triangle to test its curvature, and there are accounts of him conducting smaller-scale experiments by triangulating mountaintops in Germany. Henri Poincare, a French mathematician and physicist, offered a unique perspective on this question. He argued that it was impossible to determine the true geometry of space through experimentation alone. To illustrate his point, he devised a thought experiment involving scientists confined to a sphere world, a large sphere with specific properties. In this world, temperatures varied in a way that caused objects to expand and contract as they moved across the sphere. Poincare showed that, with the right temperature gradient, these scientists could be fooled into believing they lived on a flat plane even though their world was curved. Poincare concluded that scientists could never definitively determine whether their space was truly flat or curved, just as the sphere world inhabitants couldn't distinguish their world from a plane. For him, the choice of geometry to describe space was a matter of convention, not a reflection of an underlying truth. He believed that since Euclidean geometry was simpler, it would always be the preferred way to describe the true geometry of the world, regardless of its actual shape. This line of thinking highlighted the challenges of empirically determining the geometry of space and raised profound questions about the nature of scientific inquiry and the limits of our knowledge. It also paved the way for Einstein's theory of general relativity, which could revolutionize our understanding of space, time, and gravity. Albert Einstein, a true visionary, revolutionized our understanding of space and time in the early 20th century. His special theory of relativity, published in 1905, introduced the groundbreaking concept of space-time, a unified fabric where space and time are interwoven. In this new framework, the speed of light in a vacuum is constant for all observers, regardless of their relative motion. This seemingly simple idea has profound implications, leading to the phenomenon of time dilation, where moving clocks tick slower than stationary ones, and length contraction, where objects appear shorter in the direction of their motion. Simultaneity, the idea that two events happen at the same time, become relative, depending on the observer's frame of reference. He went on to develop his general theory of relativity, which tackled the enigmatic force of gravity. Rather than viewing gravity as a force field acting within space-time, Einstein proposed that gravity is a consequence of the curvature of space-time itself. Massive objects warp the fabric of space-time, and this curvature dictates how objects move. This revolutionary idea has been confirmed through numerous observations, such as the bending of starlight around massive objects and the behavior of binary pulsars, which are rapidly rotating neutron stars. Today, non-Euclidean geometry is the language we use to describe the curved space-time of Einstein's universe. Einstein's theories have profoundly transformed our understanding of space. It's no longer a static, unchanging backdrop, but a dynamic entity, intimately connected to time and matter. His work opened up a new realm of possibilities, from black holes and wormholes to the expanding universe itself. It's a testament to the power of human intellect to unlock the secrets of the cosmos and reshape our understanding of the very fabric of reality. In the realm of modern mathematics, space takes on a more abstract and versatile form. It's no longer confined to the three dimensions we experience in our daily lives. Instead, spaces are defined as sets, collections of objects endowed with additional structure. Often, these sets are organized as topological spaces where the concept of proximity or neighborhood is defined. This can be achieved through a distance metric, giving rise to metric spaces. In these spaces, elements are often referred to as points, but they can represent a wide variety of mathematical objects, from vectors and vector spaces to functions and function spaces. This abstract approach to space has opened up a vast landscape of possibilities, allowing mathematicians to explore spaces with any number of dimensions, curved spaces, fractal spaces, and even spaces that defy our intuitive understanding. This flexibility has proven invaluable in various fields, from theoretical physics to data analysis, where the concept of space is used to model complex phenomena and relationships. While these abstract mathematical spaces may seem far removed from our everyday experience, they provide a powerful framework for understanding the universe and its underlying structures. They allow us to explore the hidden dimensions of reality, pushing the boundaries of our knowledge and imagination. In the realm of physics, space holds a unique position as one of the fundamental quantities alongside time and mass. It's a building block of reality so elemental that it can't be defined in terms of anything else. We can't break it down into smaller components or derive it from other concepts, but that doesn't mean we can't explore and understand it. Like other fundamental quantities, space can be investigated through measurement and experimentation. We can measure distances, map out positions, and observe how objects move through space. In modern physics, our familiar three-dimensional space is seen as part of a larger four-dimensional framework called space-time. This concept, introduced by Einstein's theory of special relativity, intertwines space and time in a way that's difficult to visualize but incredibly powerful. Imagine time as a fourth dimension, perpendicular to three spatial dimensions we're familiar with. This is the essence of Minkowski's space, the mathematical model that describes the geometry of space-time. This unified view of space and time has profound implications for our understanding of the universe. It reveals how gravity warps the fabric of space-time, how time can slow down or speed up depending on your motion, and how the speed of light remains constant for all observers. In essence, space is not just an empty stage where events unfold. It's an active participant in the cosmic dance, shaping the behavior of matter and energy and ultimately the very fabric of reality itself. Before Einstein's groundbreaking work, space and time were seen as separate, unchanging dimensions. But his theory of relativity shattered this notion, revealing that space and time are intimately connected, forming a unified fabric called space-time. This revelation meant that distances in space and time are not fixed, but rather depend on the observer's frame of reference. In this new framework, the mathematical concept of Minkowski's space emerged, where time is treated as a fourth dimension, interwoven with the three spatial dimensions. But there's a crucial distinction. While we can freely move in space, our movement through time is constrained. This asymmetry is reflected in the mathematical treatment of time and space, where they are assigned different properties and signs. Einstein's general theory of relativity took this concept even further, postulating that massive objects warp the very fabric of space-time, causing it to curve. This curvature is what we experience as gravity. One of the most astonishing predictions of general relativity is the existence of gravitational waves, ripples in space-time caused by accelerating masses. These waves were first indirectly observed in the behavior of binary pulsars, which are pairs of rapidly rotating neutron stars. More recently, the LIGO and Virgo collaborations have made groundbreaking direct observations of gravitational waves, confirming Einstein's predictions and opening a new window into the universe. Einstein's theories have profoundly transformed our understanding of space, revealing it to be a dynamic entity inextricably linked to time and influenced by the presence of matter and energy. Space is no longer a passive stage for the cosmic play, but an active participant shaping the very fabric of reality. Einstein's theory of relativity not only revolutionized our understanding of space and time, but it also opened up a whole new realm of cosmological inquiry. If space and time are intertwined and gravity warps the fabric of space-time, what does this mean for the shape of the universe itself? And where did space come from in the first place? The prevailing cosmological model suggests that space, along with everything else in the universe, was born in the fiery cauldron of the Big Bang, roughly 13.8 billion years ago. Since then, space has not remained static but has been continuously expanding. The precise shape of the universe remains a mystery. We don't know if it's finite or infinite, flat or curved. However, we do know that its expansion isn't uniform. In the earliest moments, the universe underwent a period of exponential expansion known as a cosmic inflation. This rapid growth spurt stretched the fabric of space, smoothing out some of its wrinkles and leaving behind subtle patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. The study of cosmology is a journey into the unknown, where we grapple with the largest and most fundamental questions about the universe. Thanks to Einstein's relativity and the tools of modern astronomy, we continue to refine our understanding of space, its origins, and its ultimate fate. The measurement of physical space has been a pursuit of humanity since ancient times. Early civilizations developed various systems for measuring distances and defining areas, but the modern world relies on a standardized approach, the International System of Units, or SI. In the SI system, the meter is the fundamental unit of length, serving as the basis for measuring distances across the universe. The definition of the meter itself has evolved over time, reflecting our deepening understanding of the universe. Today, the meter is defined as the distance that light travels in a vacuum during a specific time interval. 1,299,792,458th of a second. This definition, intertwined with the modern definition of a second, is rooted in Einstein's special theory of relativity, where the speed of light is a fundamental constant of nature. This connection between the measurement of space and the speed of light underscores the interconnectedness of space, time, and light itself. It highlights how our understanding of space has evolved from simple measurements of distance to a deeper appreciation of its role in the fabric of space-time. In essence, the definition of the meter is a testament to the power of science to unravel the mysteries of the universe and create a universal language for understanding the physical world. It's a reminder that even the most fundamental concepts like space can be defined and measured with incredible precision, allowing us to explore the cosmos with ever-increasing accuracy and insight. Geography, the study of places and spaces on Earth, relies on spatial awareness to understand why things exist where they do. Cartography, the art and science of mapmaking, helps us visualize and navigate these spaces. Geostatistics uses statistical methods to analyze spatial data and predict patterns in the environment. Geographical space is often synonymous with land, and it can be linked to concepts of ownership and usage. Different cultures have varying perspectives on land ownership, ranging from individual property rights to communal ownership, or even the idea that land owns us, as held by some indigenous cultures. Spatial planning regulates land use at various levels, from local to international, shaping how we interact with our environment. Space also influences human behavior and cultural practices. In architecture, it dictates the design of buildings and structures.
In agriculture, it determines how we cultivate the land and manage resources. Ownership isn't limited to land though. We also regulate airspace and waters through international agreements. And new forms of ownership have emerged, such as rights to radio frequencies or domains in cyberspace. The concept of public space denotes areas collectively owned and managed for the benefit of the community, open to everyone. In contrast, private property is land owned by individuals or companies for their own use. In geography, the term abstract space refers to a hypothetical space with uniform properties, used as a tool in modeling and analysis to isolate specific variables and simplify complex phenomena. Understanding the different facets of geographical space is crucial for addressing challenges like urban planning, resource management, and environmental conservation. It helps us make informed decisions about how we use and interact with the world around us, ensuring a sustainable future for both humanity and the planet. The study of space isn't confined to physics and philosophy. It also plays a significant role in psychology. In the mid-19th century, psychologists began investigating how we perceive space, and today, it's a distinct branch of the field. Researchers delve into how we recognize an object's physical appearance and its interactions with a given space. They explore visual space, the way we perceive the world through our eyes, and the fascinating phenomena of amodal perception, where we perceive objects as complete even when parts are hidden. And object permanence, the understanding that objects continue to exist even when out of sight. Our perception of surroundings is deeply intertwined with our survival instincts. It's crucial for navigating our environment, whether for hunting, self-preservation, or simply maintaining our personal space. The psychological significance of space is also evident in various phobias related to it. Agoraphobia is the fear of open spaces. Astrophobia is the fear of celestial space, and claustrophobia is the fear of enclosed spaces. These conditions highlight the powerful impact that spatial perception can have on our emotions and well-being. Interestingly, our understanding of three-dimensional space is thought to develop during infancy through unconscious inference, closely linked to the development of hand-eye coordination. The ability to perceive depth, a crucial aspect of three-dimensional vision, is essential for interacting with the world around us. As you can see, the psychological exploration of space offers a unique perspective on how we experience and interact with the world. It reveals how our minds construct our understanding of space, how it influences our behavior, and how it can even shape our fears and anxieties. The concept of space isn't confined to the realms of science and philosophy. It's also a rich area of inquiry in the social sciences, where it's examined through lenses like Marxism, feminism, postmodernism, postcolonialism, urban theory, and critical geography. These diverse perspectives explore how historical forces like colonialism, slavery, and globalization have shaped our understanding and experience of space and place. The interdisciplinary interest gained momentum in the 1980s with Henry Lefebvre's influential work, The Production of Space. Lefebvre, drawing on Marxist theory, argued that space isn't simply a neutral backdrop, but a social product shaped by complex and overlapping processes of production and consumption. David Harvey, in The Condition of Postmodernity, introduced the concept of time-space compression. He described how advancements in technology and capitalism have altered our perception of time, space, and distance. The rapid pace of modern life, facilitated by transportation and communication technologies, have seemingly shrunk the world, making far-off places feel closer and blurring the lines between here and there. Edward Soha, in Third Space, emphasized the importance of space and spatiality in understanding human existence. He criticized traditional social theories for neglecting the spatial dimension of our lived experiences. Soha introduced the concept of third space to describe the complex interplay between the physical and imagined aspects of space, challenging the simple binary of material versus represented space. Post-colonial theorist Homi Bhabha also used the term third space, but with a different focus. For Bhabha, third space is where hybrid cultural forms and identities emerge from the interaction between colonizer and colonized. It's a space of cultural mixing and transformation, challenging traditional notions of identity and belonging. These diverse perspectives on space within the social sciences highlight its multifaceted nature. Space isn't just a physical entity, it's a social construct, a cultural artifact, and a site of power struggles and identity formation. By exploring these different dimensions, we gain a deeper understanding of how space shapes our lives and how we, in turn, shape the spaces we inhabit. habit. We've journeyed through the vast expanse of space, from its three-dimensional structure to the philosophical debates surrounding its very essence. We've explored how it warps and curves, how it shapes our perceptions, and how it's intertwined with the very fabric of our social and cultural lives. But the mysteries of space aren't confined to textbooks or laboratories. They're open to anyone with a curious mind and thirst for knowledge. By simply pondering the nature of space, questioning your own experience of it, you become part of this grand exploration. Remember, the most groundbreaking ideas often come from those who dare to think differently. Perhaps the next great breakthrough in our understanding of space will come from a fresh perspective, a new way of looking at the universe. It could come from you. So don't hesitate to observe, to question, to imagine. The history of science is filled with individuals who, driven by curiosity, revolutionized our understanding of the world. The secrets of space are out there, waiting to be revealed. Go forth, explore, and keep asking the big questions. Who knows what incredible discoveries you might make? Thank you everyone for watching. My name's The Big Y. Don't forget to drop a like, and if you're new to the Why Not family, a follow. And I'll catch you guys in the next video.